I'll demonstrate how to use an interactive simulation that models an absorption column. Now, this simulation is located at the LearnChemE site at this link. The idea of the absorption column is we have a vapor phase that has a solute in it that we want to remove. So entering here, for example, 94 parts per million of solute, leaving is 11 parts per million because what we've done is flow a liquid downward. Liquid has a low concentration of the solute, and then the concentration increases. Notice this concentration is much lower than this concentration. Note that the liquid phase flow rate is 100 times, more than 100 times the vapor or gas phase flow rate. And what we're plotting here is the solute. X means in liquid phase, Y means in the vapor phase. This is parts per million. And we have a liquid vapor equilibrium, and that's represented by this line that goes through the origin. And then we have an operating line, which is a mass balance. And the slope of this line is the liquid flow rate divided by the vapor flow rate. We're showing here as we count off stages of how many stages it requires to cause this type of separation to decrease the mole fraction in the vapor phase as we increase it in the liquid phase. And the simulation allows us to change the pressure, change the temperature, change the inlet concentration of the solute, and the inlet vapor mole ratio down here, and the solvent flow rate can also be changed, and then the desired molar flow rate leaving, how much we want to decrease the parts per million of the solute. And then this simulation also has an example with 5 stages that shows a little more details, and we can look at what's the minimum liquid flow rate that we need. So L over V, the minimum value, in order to affect the separation. So let's look at the simulation. So the simulation has details. It shows the mass balances and the equilibrium expression we use to determine the number of stages. And then here's an example where we take a large number of stages, but if we were to increase the pressure of the gas phase, then we're providing a bigger driver force for absorption into liquid phase, and the number of stages decreases. Contrast, if we increase the temperature, now we lower the concentration in the liquid phase of the solute, so the number of stages increases. So we can change the inlet concentration of liquid, inlet vapor mole ratio, the solvent flow rate. If we increase the solvent flow rate, we decrease the number of stages. And then the desired outlet mole fraction. So if we go to a higher value, we have less separation. Of course, then it takes less stages. Here's the minimum value of liquid over vapor, and that's shown here. And then we can select this. Now, this is specific conditions, and the point of this is to show that as we move down, the parts per million of solute in liquid phase increases in each stage, and the parts per million of solute in the vapor phase decreases in each stage. And if we pick a stage, so we pick up here stage 2, then it shows the details of what's the flow rate of moles per hour of solute into and out of that stage. Now it's flowing in the vapor phase, is flowing out in the liquid phase. Well, these numbers are the same because we're at steady state, so we can't increase the solute concentration. If we look at a different stage, of course, these numbers change, and they're getting higher as we move down because we have a higher flow rate in the vapor phase and we have a higher flow rate corresponding to the liquid phase. So the idea of an absorption column is to remove a solute, impurity, contaminant from a vapor phase and put it into a liquid phase so we can do subsequent separation.